Okay, we're rolling. We are going to part 4. I wasn't planning it, but I like to keep all my thoughts together in one bunch. This kind of ties back to the part 1 about the red point, red shift, whatever. And I'm more or less going to throw this out to you people out there, maybe some of those that are more in the know. Maybe they can get back to me on this. And so I'm more or less going to set the stage here, present it to you, and hopefully we'll hear an answer. What we have here is steel with a melting point of about 2555, hard steel, copper 1985, titanium just a little over 3034, and carbon around 7,280. So that's probably closer to the sublimation point of carbon. Because carbon doesn't melt, it goes from the solid state directly into the vapor state, and I've been seeing this. You know, a lot of times in the pipes, they'll start off with a rod like this, and it will actually sharpen this rod like a pencil. And these rods will reduce down to where they get very small. So is it the vortexing or the physical spin of the or the action of the flame causing the carbon to disintegrate or melt? Or could it be that the carbon is actually heating up past 1800 degrees? And that's what gets me. You get all these metals here: copper, steel, titanium, and carbon. And according to the books, when you get the orange state, it's supposed to be all equal at about 1800 degrees. Then you have the yellow band. It's between around 1900, maybe close to 2000. When you get into white, then you get over 2000 degrees. So if we can, if we say that we're actually producing a white band here, we know that we're at the melting point of steel. We are past the melting point of copper, and we still got a long ways to go as far as titanium, and much longer to go concerning carbon. And so does this mean if all four of these are equal at the orange point, the transition color of orange, or 1800 degrees, does that mean that titanium and carbon have a vastly extended white point, or yellow and white point? But we're talking a good 2000 degrees over that of copper, 3 times the heat, so to melt it. So what's going on? Is titanium and carbon, are they an exception to the rule? So when this piece of carbon, when it heats up to a nice shiny bright orange, what is its temperature? I know that you can take carbon and hold, if you had a couple hundred amps from a battery, you could connect both ends. And this carbon would heat up nice and red. This one time where that's all they used was carbon lamps. And if you had enough juice, this thing would turn white, and you'd actually have a light. And so it takes a lot of juice to do something like that. But that temperature, that light would not only produce it'd be very bright, it'd be very hot. It'd be producing a lot of thermal energy along with the proton energy of the light itself. So what's going on here, with the carbon and the titanium? And that's why, or it could be the reason why in the, I think it was video 87, where I had the titanium inside the joe pipe on a vertical test, where it heated up, but it also caused the heat of the joe pipe to get a little more red on the outside. So could it be that the titanium was getting hotter than the actual steel of the joe pipe? If that's the case, then this rule doesn't apply. It's not conclusive to everything. And if that's the case, imagine the potential that you could do where you could use titanium as a liner, or you could use, say, ceramic or porcelain as a liner to increase the output heat of the joe pipe. And at the same time, it's going to protect it. And the ceramic will probably be better because it's not going to oxidize, and because of the contact with the oxygen and the nitrogen in the air. And that's why you get oxidation in the first place. You know, that's why you get rust. In this case, steel. So titanium would work, maybe taking titanium and putting a ceramic coat on it would probably work really well for a heat pipe. And so I have to ask these questions. Now, if you got ceramic bonded to titanium, is the ceramic going to get hotter than the titanium? Or you might have a carbon liner. Will the carbon liner get hotter than the pipe that it's seating in? You know, you have to ask these questions. So someone out there, I know, is going to have an answer that's going to help give me a little more focus on that. And that's all I wanted to bring out. And this is going to be the fourth installment in this series here. Thank you.